So now that we know what vector fields are, why don't we take a look at electric fields? So we're going to first define what an electric field is, and then try and get a mathematical description of the electric field. So let's start off with the definition of an electric field. So an electric field, commonly abbreviated to E field, surrounds an electric charge and exerts a force on other charges in the field. And it can either attract or repel these different charges. So now that we've kind of defined what an electric field is in general, the next question would be, how do we even measure this? And to measure this, we're going to take a look at a point charge Q in space. So let's look at a point charge Q in space. So I'm going to say this is my point charge Q. And I want to look at a point P. So let's say a point P here. Oops. So there's point P, and that point is going to be a distance r away from Q. And remember from before, the unit vector for r is going to be in the direction from Q to P, so wherever the point source is towards where we're looking from. And now we want to bring in a positive test charge Q at point P. So I'm going to turn point P into red to represent a positive point charge Q. And that means I can now observe a force due to the source, capital Q. So we're going to define the electric field due to Q at point P as the force per positive unit test charge, assuming Q is very small or Q is really close to 0. So this electric field, in order to calculate it, I know that I need to still be able to draw out some electrostatic force happening at point P. So if I have this point charge Q in space, a distance r away from little q, then little q, because it's always positive, just so that we can compare different things, it's going to experience a force acting from Q onto Q. But because we only are looking at 2 points, we can just say this is FQ. So if we want to define the electric field a certain distance r away, then it's equal to the limit as Q approaches 0 of the electrostatic force experienced by it divided by its charge. So that means it's going to be the limit as Q approaches 0 of K QQ over Q R squared in the direction of R. So another way of writing this, to simplify it, would be ER. The Q's can cancel out, just like this. This gives us FQ. So like I said before, we're only looking at the test charge plus Q over here. So I'm just going to take away one of the subscripts because we already know what we're looking at. So we have the force from Q divided by the charge of the test charge, which is equal to Q over 4 pi epsilon naught R squared, R hat, and this is in newtons per coulomb. So let's just outline this because this is important. So just remember, I've represented it as Q over 4 pi epsilon naught R squared. That looks like a V. Oops. And K is equal to 1 over 4 pi epsilon naught. One thing to note is that N over C is newtons per coulomb. Engineers use volts per meter, so we won't really go into that until later on once we understand electric fields and a few more different types of calculations. So now we have our definition of an electric field. The next question I want to ask is, what if there are multiple point charges? So this basically means if I don't just have my test charge, my charge capital Q over here, what if I had Q1, Q2, Q3, and I had to figure out the electric field at a point P away from all of that? So the electric field at any point is the superposition of electric fields due to individual charges. At that point. Which means I can rewrite my equation for electrostatic or electric field by having the total electric field, so E total, is equal to the summation from n equals 1 to n equals n for the total number of charges that we have, of En. So that would essentially be equal to E1 plus E2 plus E3 plus however many more there are up to En. Oops, I forgot this. It's a vector. So although we can just say the principle of superposition holds for electric fields as well, the one thing I want to bring to your attention is that the electric field is a vector. So that means, similar to electrostatic forces, when you're adding it all up, if you have Ex, Ey, and Ez, you have to take all of those into account because the electric field is a vector. So we have to use vectorial summation